Good evening, ladies and gentlemen. Can I have your attention, please? Welcome to tonight's monthly AIW New South Wales event. Normally, our state-based lead, George Nicholas, would be up here doing this introduction, but he's actually sick today, unfortunately. So he sends his apologies. He wishes he could be here, but the show must go on. So we're all here to learn about some basement waterproofing, so I don't see any reason to delay that. And that being said, allow me to introduce Sam Parker. Please give him a warm welcome.
Thank you, David, and good evening, everybody. And it's great to see such a big turnout. Actually, I wasn't expecting this many people. Must be because I want to see David's beautiful face. This slide's been up for about 20 minutes. I'm just wondering if anyone's figured out what it says. It's just yes.
It's waterproofing of low structures.
Very good. And I'll wait for evidence is proof. Waterproofing of below ground structures. Very good. Excellent. There's a prize for you later. Ah, God, this thing's too fast. Okay, so I'm going to be talking about some design considerations for below ground structures, making them watertight or waterproof, depending on which words you're accustomed to. We're going to go into a little bit of a detail as to the definitions of the two of those. We're going to go through the function of concrete tonight, talk about what's waterproof versus watertight, where you might find typical issues in below ground structures. I'm probably getting in your way, am I, Pedro?
Oh, okay.
You can see through me, that's good. What does waterproofing data look like? We'll look at some examples, some standards which might apply or might not apply. And we'll discuss the concept of the codes or standards acknowledging the difficulty in actually getting below ground structures, particularly if there's a water table present, getting it watertight. And then we'll go through the different forms of barriers that can be installed in a below ground structure. The next few points, crack mitigation, preferred shell design. Those are topics I normally talk about to predominantly engineers. I think tonight we've probably got a pretty varied audience type. We might have some suppliers. I've seen some suppliers, lots of builders, maybe some engineers, some architects potentially. So I'm probably not going to talk too much about that, and I do need to leave David quite a bit of time for his fun stuff. Mine's boring and theoretical, and his is the good stuff. Hopefully I'm not going to put them to sleep, David, before you get to talk. I'll show you some typical design mistakes or installation mistakes. And that's about it. So function of concrete. Concrete's got many different uses, obviously. It can be used for structural robustness, for fire resistance, for acoustic resistance, thermal. It's got great thermal qualities, aesthetic qualities. It looks pretty good when you get it right. It looks pretty terrible when you get it wrong. But we're going to talk about its water resistance, in particular for below ground structures and basements and tunnels. All right, so waterproof versus watertight. Waterproofness is defined as the quality of being impervious to water or vapour. So if it's in a liquid or a vapour state, it's impervious to that. Concrete, by nature, is never actually waterproof. Water or vapour can always go through concrete, depending on how the density of it and the thickness of it. It might stop from manifesting on the other side, but just as a pure product without the enhancement of additives, it's not actually waterproof. It is watertight though. It can be watertight if it is installed properly. Then we get this concept of water, stopping water, resisting water, so that it doesn't manifest on the functional side or surface of your structure. So typically, when things go wrong in a basement, and who here has been involved in below ground structures that has gone horribly wrong? Be honest, come on. No, I don't believe you, come on. Still don't believe you. Oh, whoops, what's happened here now? By far, joints, improper placement and improper detailing of joints is the biggest cause of water entry into a basement. Typically around 40% of issues you can attribute to joints or problems with joints. And thereafter cracks, and in particular cracks which weren't intended. When we design concrete, we actually expect the concrete to crack. We try our best to make it crack where we want it to crack, but then concrete says, no, I'm my own man, I'm going to do what I want, and I'm going to crack where I want, and you did your best, but I'm better. And so unfortunately it catches us out quite often. That's about 30%. And then defects such as honeycombing, bad, not vibrating concrete, that's around 18-20%. Penetrations, not detailing around penetrations is another problem, around 10%. And then just bad quality concrete, very porous concrete, 2%. Oh, okay. Now, are you able to start that one there?
I can.
Yeah. So that is a column inside a basement.
Yep, I think I hit the leak.
Yes, they definitely hit the leak. It's not a perimeter structure, so if you can imagine this room being a basement, the column is sitting here, it's above the hydrostatic slab, that hole's drilled about 400 millimetres above the hydrostatic slab. That is 70 MPa concrete. We drilled a hole through that column, and that's what happened. Next one.
Oh. Hold on.
Okay. That's a basement slab, just in a normal single level basement, resi basement. They designed it to be a drained basement. After heavy rainfall, the drainage layer wasn't able to actually redirect the water fast enough, and it was manifesting through the joints. Next one. That is a diaphragm wall. That is a retaining wall structure. It is about 1.5 meters below the water table. That wall goes down another 25 metres. That hole was drilled right at the top near the ground level. That's the amount of water that was coming through even at that level. Just to give you some idea, the amount of pressure that water would put on a structure per square metre would be equivalent to, if I were to amortise it, if I were to have a steel plate, and I could hold it up like that, very stiff plate, no weight to it, it's a magical plate, it's got no weight but it's very stiff. I could place, say, a typical Toyota Corolla on top of that plate, and another one, and another one, and another one, and another one, 6 of them. 6 of those cars would be the equivalent pressure per square metre than that 1 metre of water head pressure exerts on a structure. Next one. Hey. You can see there a construction joint. They did put some waterproofing in there, they put some hydrophilics in there. They didn't know how the hydrophilics worked. It went terribly wrong, and now they've got a water feature which they didn't have to pay for. It's fantastic. Some basements that have gone very, very horribly wrong. I see there are a couple of my current staff, or more than a couple, my current and ex-staff sitting in the audience. That's actually our office. That's actually our office, basement, lowest basement level. We lost 3 cars, got written off after that event. So yes, it can go horribly wrong if you get it wrong. Most of you probably know that there is no Australian standard for the design of below ground water resisting structures. There is no standard. I'm flabbergasted by that we're in 2024 and we don't have a standard that guides us to how to design watertight below ground water resisting structures. So we have to depend on AS 3600, or we can use AS 3735, which is a design standard, but it is related to water retaining structures, so tanks. There are many concepts that are transferable from resisting to retaining structures in any case. And with any below ground structure, you should also consider 4654.2 is actually part of the design documentation that you will need, because the basement will have a lid, will have a top, a podium slab, transfer slab, whatever you want to call it, and that's where you're going to need to design to the principles of 4654.2. So the two have to interact. In the current standard and any current NCC, BCA, and previous versions to it, and David's going to talk about what's coming next year. But as of today, as we speak here, the NCC actually provides an out for Class 7 structures and Class 8 structures. You won't be able to read it potentially except for the ones at the front, but it says here FP 1.4 does not apply to Class 7 or 8 structures. And F1P4 it says moisture from ground must be prevented from causing undue dampness or deterioration of building elements and unhealthy or dangerous conditions or loss of amenity. But then it says, but by the way, it doesn't apply to Class 7 and Class 8. David will talk about what the future looks like for us. So what we have to do, because Australia doesn't have a standard, we look at overseas documents for guidance, and there are lots of them. There are over 7 design standards overseas that we can get from overseas that we can use. I've listed some of them there. The most popular by far is BS 8102, that one. And that started off as a code of practice in 1973. It's actually still retained, like the phrase code of practice is still retained in the title of the document, but it's no longer a code of practice. It actually is actually a standard. It became a standard in 1990, and then it got revised in 2009, and the current version is 2022. In 1999, there was a Supreme Court case in the UK. It's commonly known as the Outwing case that had immense implications on the design of below ground waterproofing structures. So to cut a long story short, a builder engaged a subcontractor to do the design and installation of a basement, and they did so by virtue of a bonded single layer membrane, and then the builder who engaged the subcontractor started backfilling, but what they did is they put the ag line sort of halfway up the wall instead of below the slab level, and it started to leak. And so the developer or the principal contractor stopped paying the subcontractor, and the subcontractor took them to the UK Supreme Court, and the developer argued that, well, we paid you to install a impermeable waterproof membrane and you completely tanked the structure, so it doesn't matter where we put the ag line, because your membrane should have done all the job. And the builder, subcontractor argued, sorry, I don't know how to get rid of that, argued, well, no, the membrane's there to help, but you can't just rely on the membrane. So the two went back and forth in the Supreme Court, and the judge basically said, listen, there is no way that we as humans can actually get a basement waterproof just relying on one system. It's impossible. It's not like we are doing microsurgery with the best tools and microscopes and whatever in a controlled environment. These are sometimes mega sites. You've got people that might be trained and some not so well trained, and things happen. And so you've got to expect that things will go wrong. And so you can't just say that the membrane should have done all the job. You should have actually installed backup methods of protection other than the membrane. So from that came the revision in 2009 and 2022 that basically had the concept, or adopted the concept, that don't always have ancillary or secondary or tertiary methods of protection beyond your primary method, whatever that primary method might be. These are two extracts of two different standards. Again, it'd be hard for people at the back to read, but let me tell you what it's trying to say is it's trying to tell the reader that expect in a basement that there will be some water that comes through. Expect that there'll be some water that comes through. So expect that you're going to need to go back and do some remediation. There are a couple of ways that you can avoid or minimise that likelihood, and we're going to go through that, but the datum point that you start at is that expect that it's going to come through and that you're going to need to do a little bit here and there, as opposed to starting from the datum point that we're going to walk away from here knowing that nothing ever is going to happen to this basement. This is a little sliding scale of dryness that I prepared a long while ago. It tends to convey a pretty good message. The British Standard 8102 talks about 4 different grades, or 3, but the first one split into 2. In the 2009 edition, and even before that, it was there were 4 grades: grade 1, 2, 3, 4. Now it's grade 1A, 1B, 2, and 3. Grade 1A and 1B. Well, 1A basically means that you can have a basement where you accept that there might be some running water, and obviously dampness as well. But you might have a wet wall scenario. Grade 1B would be where you can't have running water, but you might have dampness. Again, that could be a wet wall scenario, for example. Grade 2 is where you've got no. How are we going for time? 20 minutes. I'm going to speed up. Grade 2, where you don't have any running water or dampness. Basically, the concrete looks dry, but it might get affected by RH, relative humidity, inside the structure. Grade 3 is where you're even controlling the inner environment using dehumidifiers or air conditioning units. You might use that, for example, in museum, for example, where you can't store paintings down there. The Mona Lisa is going to look like Krusty the Clown drew it probably after two weeks or something. Type A barrier system in the standard talks about putting an external or could be an internal barrier. I've shown that there's an external barrier. There's your basement structure before. You got water on the outside of the structure, and because they didn't protect it, now they got water inside as well. But then the guy next door put a barrier outside the structure, and somehow miraculously got it perfectly correct, and now you've got a dry basement inside, type A. Some examples of membranes that might be type A. The one on, I don't think I've got time to go through these. That's a Tremco product, HDPE and bentonite. Next one's pure bentonite. Next one's PPE, PE. Next one's butanol. Next one's HDPE. Next one's FPO. Next one's SBS. Next one is PVC. There are lots of products out there. Let's just leave it like that. Some examples of how it might look like installed. The top left-hand one is the Fosroc product. It's called Engage, and it's PPE, PE, PP and PE product. Next one is a bentonite. It's a clay which swells when it comes in contact with water. Bentonite's a naturally occurring product, typically from China, but now also from US and a couple other countries. Those are bonded systems. These two are unbonded. You might use these typically in tunnels, but it doesn't mean you can't use it in basements either. These are Soprano products, Flagon. That's a SBS styrene butane styrene product, bitumen-based, around the pile cap. That's the hydrostatic slab, or hydrostatic slab's going to go on top of that. And that's a pile with some waterproof grout around it. Type B is where you make the concrete itself watertight by putting additives in it. But additives will work well if the concrete has been placed well. If there are large cracks which form in the concrete, or there are voids in joints which move a lot, the additive can't do much there, so you've got to add with the additive, we've got to supplement the additives with particular type of waterproofing barriers in the joints, like hydrophilics and water stops and so forth. Here are some examples of those. That's a solid strip of a hydrophilic which sits in a joint. The next layer of concrete's cast on top of it. If water tries to go through that joint, the hydrophilic will swell, close that gap up, and water shouldn't get through. That's a reinjectable hose which sits in the joint, and you inject through these injection ports. Different types of products, could be hydrophobic, could be hydrophilic, could be grout, cementitious grout, depending on the type of structure, and it fills up the gap. That's a gunnable hydrophilic. It swells again with water, same as the other one, except it's gunnable. Some puddle flanges that might go around a peno. There's a water stop in a PVC water stop. You can see it here being installed over a joint. The idea is that the little circle you see there, I wish I had a laser or I was taller, one of the two. That circular bulb there, that actually gives way, it breaks as the concrete moves, but it still maintains a continuous impervious layer so that water can't get through. Okay, so we talked about the additives there. There are basically two branches of additives. There's the permeability reducing admixtures for hydrostatic cases, and then for non-hydrostatic cases, PRAN and PRA. So where you've got low water table, like below half a metre, or no water table, permanent water table, you might consider using the non-hydrostatic type of admixtures. These are typically soaps and fatty acids, hydrophobic. They basically repel water. And then in the hydrostatic cases, you'd go to the densifiers. You'd put some admixtures into the concrete to actually create smaller micro void spaces in the concrete, making it denser, making it harder for water to go through. And then you've got dendritic types of admixtures, crystal forming. Here's a picture of what something might look like. And the ACI consider that the crystalline type admixtures, dendritic structures, admixtures are the most efficient, followed by hydrophobic pore blockers, and then the colloidal silica type of admixtures. Here's a time snap of a crack which has formed in concrete that's had some admixture in it. It's shot over 33 days. That's the 33rd day. That's how it starts at 0.27 wide, and by the 33rd day it has healed. That doesn't happen often, by the way. It's nice when it looks like this in a lab, but in reality it doesn't quite always work that way. Type C is a drain structure. So I talked earlier about accepting that a structure is going to actually leak. Make that your datum point and design from there. Well, with this type of system, that's the hydrostatic, the outer shell. You're accepting that water's going to get through, and you build another inner structure that the water buildup can never actually manifest above or inside that level. So the water has got in. It's definitely leaking. It's just we can't see it, and so we accept that. Oopsie daisy. That would give you at least a type 2, and if you were to control the environment in here as well, you could get to a type 3, grade 3 basement. Just an example of some of the design detail that goes into the design of a deep basement. It's not simple, draw little lines here. You do need to go to a specialist. There's a lot of detail in that. You're not actually going to see any of it, but all those colours are different products interacting different ways, and they're all waterproofing elements. Example of a type C design being installed. That membrane is sitting on top of some drainage cell. So it's basically sitting, this is the drainage zone. It's sitting up here. Whoopsie daisy. And so on top of that will be another slab which gets poured, and that's your wearing slab, which should be totally dry. But if we were to look below that layer, that's what we'd see. Hydrostatic slab. The drainage cell sits on top of that. That's the membrane, and then again, I wish I was taller. That's the membrane which sits, the slab which sits on top of that. Type E is, why is that not coming up? We lost the drawing.
Is that what you want?
I'll go back one. Yeah, we lost it. Go again? All right. This you won't find in the standards. It's a Sandparker special. So this is for those that have some background or know a little bit about cathodic protection. It uses the same principles as that. You basically grind in some grooves in the concrete that's got wet. You install a ribbon anode in it. You connect it to a power supply or a battery. You install a cathode outside of the structure, and you zap it up and the current flows through and electrically charges the water in the structure, makes it positively charged, and it pushes that water that's in the structure towards the cathode. So there's a section of a basement, that existing basement, that was getting water in it. We put the anodes in, and that's what it looked like after, once we put the battery on. I'm not going to talk about this stuff too much because that's more engineering related. I need to give David time. He's getting nervous. I can see him through the corner of my eye.
You're just past 30, you're not too bad.
Okay. Maybe I did a little exercise using different standards to see if I designed a structure using 3600 or 3735 or BES EN 1992, part 1 or part 3 or Syria C6660, what it tells me in terms of how much steel I need to put in and what expected crack width I might expect. The bigger the cracks, if you remember, the more problems we're going to have. And surprisingly, I found that 3735 was the most conservative. Again, I'm not going to go into this, it's too engineering related. This as well. That as well. Okay. Here's an installer. That's it. Put a reinjectable hose in a construction joint. That's my hand. You can see how beautiful it is. It's definitely mine. And you can see that it's a good 80 millimeters, 90 millimeters, 100 millimeters away from the joint. If the resin can't get in the joint, all that hose is doing is pushing the resin from one end to the other. Those hoses have got little slits in them. There are two hoses, a hose within a hose, to create a one-way valve. You inject it with pressure. The pressure causes the valves to open, and it leaks out of those valves into the joint. But if it's fully surrounded by concrete, it's not doing anything. To have a little section like this that's away from the joint's okay. Like when I say little, maybe 400 millimeters, up to 400 millimeters. But if you've got long sections, there's no resin going in there. Here's a water stop that's been placed in a construction joint that will be formed. Where I've got the two red lines, that's actually where the joint is. And you can see the installers did a fairly good job, but they didn't quite install the bulb exactly where the joint is. So that thin section of the PVC water stop will tear, and that joint will not be waterproof. You've got to get it perfect. Here's a hydrophilic which has been installed too close to the edge. That's a wall, that's a slab. That should have been installed deep into the concrete wall. They put it too close, it had no cover. Water got to it, it expanded and basically blew the concrete out. Effectively, I did an engineering calc on the hydrophilic. Its expansive force, it is able to induce the same expansive force, an equivalent expansive force as a 40 MPa, as a splitting tensile force of a 40 MPa concrete. So in other words, for anything at 40 or less, if that hydrophilic is not at least 70 mil away from the concrete edge, from an unrestrained edge, it's going to basically cause the concrete to spall. Here's some epoxy grout that they built up 300, that's waterproof grout which, let me rephrase that, grout which is impervious to water. Grout, particularly epoxy grout, is very exothermic as it cures, as it hardens, very high heat, which gets generated, and that causes it to crack if you don't design it properly, or if you just think I'm going to fill a whole big section of, deep section with grout or epoxy. Concrete, when it comes out of a truck, typically is around about 30 degrees. And when it goes through a curing process, if it's say a metre deep, which you might find in hydrostatic slabs, or even deeper, even thicker, that concrete, whilst it's hydrating, can get up to 80 degrees. 80 degrees is, you can actually fry your eggs on it. That's some steel that's been designed to AS 36, 37, 35. How is the concrete going to get in that? I had a couple of other images earlier, which I'll flick through really quickly. There. That's not steel that's come off the truck. That's the steel places that have placed the steel. How on earth is concrete going to get in there? But that has been designed to 37, 35. And people haven't thought about, because on paper it looks, we've got 100 mil spacing and the aggregate will get through there and the concrete matrix will get through there, no problems. But where you've got laps, because steel come in certain lengths, you're actually doubling it up. And so you lose that space that you don't see on paper. You think it looks good on paper, but in reality, you end up with the concrete just say, I give up, I can't get down there. Aspros, bar chairs. Now that's meant to be a bonded sheet membrane. Bonded's really good because if there's a puncture, then the water can't go anywhere because the membrane's bonded. But then the doofers have gone and put Aspros in a line, connected. So basically, you've got all these grids where the concrete hasn't been able to bond the membrane. And so you have a leak here, it could travel basically all across the site. Very smart designer decided to use permanent formwork in a construction joint. How on earth do you waterproof that? My God, that was a $1 billion project. Not $1 billion worth of thought they went into that one. Contamination in the water. We took a core out of the concrete. That was the colour of the concrete because of the pollutants in the water. And when it dried, it went that colour, back to normal concrete, but the pollutants stopped the membrane. I'm not going to mention which membrane that is. It wouldn't stick because of the pollutants. Yeah, that's the video. I'm not going to show you that because I'm going to give David his time, and that's probably 40 minutes or less.
Yeah, spot on.
Okay, there you go. Are we doing questions now or after?
I think we can do them after. I won't take very long, so we can, yeah. Thank you. Just let me swap this over quickly. Okay, tough act to follow. I'm not actually talking about presentation, I'm talking about your immaculate beard. Makes me feel naked up here. But look, I'm going to do, we actually didn't coordinate at all for this, so I sort of thought, look, I'm going to take things a little bit left of field, present things in a little bit of a different way and really get everyone thinking about different scenarios and case studies, right? So I put together a few things here. That's the slide about me. We don't need to go into that right now. I find that it's very helpful to start with really basic concepts that apply very broadly before you narrow things down, right, and start talking about specific things. So I thought, well, what's the most basic principle I can think of for basement design and keeping the water out of the building? And I came up with this equation, which is the protection that you have minus the exposure equals the performance of the system. And protection, Sam went through a lot of different systems, type A, B, and C protection measures. There's so many of them. When you evaluate those, and then you evaluate the exposure, which is normally your hydrostatic risk or geotechnical considerations, even the size and shape of your structure can inform that as well. So you take your protection, you minus your exposure, and that's how well you can expect it to perform, right? So let me explain that in a little bit more detail using my current favorite thing, AI-generated images. So for this, we're going to imagine that we have that little village there and we need to protect the village, right? Like that's the internal space. We want that to get the good outcome. That's our performance. And I'm using this scenario. So in this image here, our protection is our massive concrete wall here, right? And our risk or exposure is our relatively small and calm ocean against that. So if we were to give these a rating out of 10, anyone want to pick a number, what you think that concrete wall would be out of 10? No? Any volunteers? 10? Well, I don't think anything's a 10, so I actually went with an 8 on that one. And then our water's pretty low, right? Pretty calm. It's a 3 I put on that one. So when we apply our equation, what do we get? We get a 5. And I should have mentioned, by the way, the higher the number, the better the rating, right? So if we've got a 5, that's pretty good level of confidence, pretty good level of performance, and confidence that that performance will be achieved. So comparatively, have a look at this one. In this, our risk is our massive wave, and here is our protection. Does anyone want to have a guess what we would rate our protection in this scenario? 0, come on, this is still standing up. We'll give it a little bit of something there. The reason I asked this question in this scenario is that we actually have 2 lines of protection here. Not that it's doing very well, but we have 2, and I gave them a 3 down on the bottom end. You know, it might be a 2, might be a 1. And we've got our wave as a 9. So then when we apply our maths to this, 9 minus 3 minus 3, I messed that up, didn't I? So I was putting this together last minute this afternoon. So the maths was wrong, but the outcome is correct. We would, because there's such a high degree of exposure and we have such little protection, we actually get a -3. So because that's below 0, we have almost a degree of confidence that it actually will underperform and that it will fail, which obviously this village isn't going to do too well after this lands here. So now that we've got that principle in place, I've got 4 examples here, and I actually wanted to get Sam back involved a little bit in this one. And we're going to bring up these 4 examples, and we're going to talk about, well, what types of protection can we see that are involved here, and what grade of performance would we expect that this might achieve. So, Sam, do you have any thoughts? I'll just recap this at the moment, what we're seeing in this section. And before I do, I will say that the reason you will see all of these sections are the wall-to-floor junction is because I've found that you can understand 90% of how a basement is going to be designed by looking at this junction. Everything else is accessory. If you get this right, you're just filling in the little bits and pieces after. So what we've got here is a soldier pile wall, and we have like a mega flow drain in between those soldiers. Then we have infill with shotcrete in front of it. We do actually have a waterproofing system under the slab here. That's not a... Oh, hold on. No, it is a vapor barrier in this instance. I'm thinking of the next one. So then we have a drain on the inside here. So we've got our first line of defense of the mega flow. We've got our shotcrete wall. Doesn't have any additives or anything fancy like that in it. And then we've got our cavity drain on the inside. Sam, what do you think about this? And what grade of performance would you be confident that could be achieved by this particular design?
It depends on whether there's a water table, permanent water table, or not, or whether there is a perched water table.
So Sam's saying it depends on whether there's a water table or not. And just for this scenario, we'll say that all of the designs we're going to have don't have any permanent water, but when it rains, the geotechnical considerations, there could be a bit of temporary hydrostatic pressure against the wall.
Yeah, so I assume that that would be the case, but maybe some people might not have. And the dead giveaway for that was the drainage cell, because if you've got a permanent water table, then it's pointless putting drainage cell, right? Because it's always full of water. We've got a vapor barrier here. It's not a waterproof membrane. A vapor barrier, according to the standard 2870, it can just be a 0.2 millimetre, 200 micron thick piece of plastic that the laps have to be taped or overlap a certain length. It's there actually to stop condensation and to help during the curing process of the concrete. So I would say that if there was a water table that developed, and if it was a significant water table, a temporary significant water table that developed, potentially if there are cracks in here, it might find its way through a vapor barrier. Potentially, if this overflows, it could get in here, but that's a lot of potentialities.
What would you be confident grade this would achieve, and what sort of space could this be used for with that grade?
I would say that it's absolutely a 1A, definitely. It might be a 1B. I wouldn't give it a grade 2. I would be happy to use something like this in a structure that hasn't got any functional areas other than car park spots, and where there isn't a permanent water table. Other than that, though, I would be inclined to add some additional protection measures. That's my personal.
Hold on to the mic. We'll go to the next one. So that's actually exactly what I would think. We haven't rehearsed this at all, so I'm really putting him on the spot here, but that's exactly the scenario. Okay, so this one, just to explain, this is actually a sheet metal pile shoring wall, and that's what this is here. This is the sheet metal pile, and then it's got void formers in it to take out that contour of the wall. Then our blue line is a type A barrier system, and lastly, we've got a water stop in there as a type B measure, but that is the only type B measure. There's no additives or anything like this in here, so it's just a little bit of a secondary type B there. No perimeter drain or anything on the inside. What are your thoughts on how this will perform in a sort of moderate hydrostatic risk environment?
I would say that this is a design that intends to be installed where there is a permanent water table or significant or often reoccurring perched water tables, because there is no drainage behind the wall. 8102 actually requires you to put drainage there if it's only temporary or no hydrostatic pressure, permanent hydrostatic pressure. So that tells me that there's permanent hydrostatic pressure. We've got a waterproof membrane. Hopefully it's been installed properly and it's a good quality. We've got the primary. We've got a secondary measure, which comes from the type B. So it's type A. That's part of type B. You're going to rely on the concrete being fairly well placed as well. So that's going to give you some protection. It's definitely going to give you at least a type 1A, at least a type B potentially if it's been placed well. If you're lucky, a type 2. But I would never, if there's a permanent water table, I would never install a basement slab without at least a spoon drain or a hob as well. And that comes back to that concept where I said your datum point should be that it is actually going to leak.
Okay, very good. I would just add one more explaining factor is that a lot of these type A systems, when they're installed like this, especially if it's against like a pile wall of some sort that can be quite rough, the manufacturer will require you to have what's commonly called a shear panel in there to create a separation, so that if this structure does move independently of this wall, it's not grinding the membrane against that. So it's a separation like a slip sheet or something like that. So good thing to know. Okay, This one we got a little bit more elaborate here. So if we start over on the left-hand side, we've got an area which has been backfilled. So there is, unlike a shoring wall, like a secant pile or anything like that, we did have access on the back side here. Structure's made of a permanent formwork, core filled with concrete. We've got waterproofing and drainage cell on the outside of it. And then we have an actual accessible, they call it maintenance passage, or plenum is a common word as well, which is also drained on the inside here. And then to add on top of that, we've actually got what looks like an indoor facade here, where we've got a cladding and top hats and presumably sarking and everything here. What are your thoughts on this one, Sam?
So if I were to look at that side of it, then this is going to give you at least grade 2, and you might be lucky with the grade 3. If I were to look at this, then it could be anything, right? Because what they've done is they've considered, I'm assuming here, or did you say we've got drainage cell?
Yes.
Okay, so there's not a permanent water table here. I mean, I don't see that there's an issue with this design, but if you were to ask me what type of grades you might get at this allows that wall to be grade 2 at the minimum, potentially grade 3. That particular design there allows that area to be anything from 1A, 1B, 2. And ultimately, if something goes wrong, that's what they're going to be looking at. So for me, I would consider that that's not going to give you anything, that's not going to give you a grade 2 unless you're lucky.
Okay, so just a question, or two separate questions here really. If we're looking just at our horizontal transmission here, what's standing in the way with this design of calling this grade 3 based on the protection measures we've got in place?
So grade 3, if we recall, grade 1A is where you can have seeping water, you could have running water, you might have drips of water manifesting here. Grade 1B was where you don't have running, but it might be damp. You might see there's a damp patch there. Grade 2 is where you don't see running water or dampness, but there might be some condensation that forms in here. Grade 3 is where you're not only are you controlling those surfaces, but you're actually controlling the internal environment as well. So, for a typical basement, we might get a type 3, but if you were in a basement where there's actually quite a strong airflow that can come from high RH air, you won't get a grade 3. You'd need to control the air quality as well.
Would the plenum be ventilated?
Yeah, I mean, typically plenums are ventilated, yeah.
So that
because
would reduce the humidity in the music room there? Or the condensation?
potentially. I mean, plenums are just recirculating air. So if the outside RH is the same as here, it's not going to do anything. It's the plenums are there, as you would know, just to get rid of the carbon dioxide from the cars and whatever, and to circulate that sort of air out. But if it's pulling air from outside, which is the same RH as in here, then it's not doing anything.
Say if that was a wet wall, because a lot of basements have the wet wall in the plenum, and then they've got like a block wall on the outside.
Yeah.
Does that act as like a drying passage kind of thing?
It can do. I mean,
What would that be? What class would that be?
which area are you talking about?
Like if there's a wet wall,
Yeah.
what would that be? What standard would that be, the grade?
Well, you wouldn't even be talking about that. If you've got an inner wall, then we all agree as a community that that's what we're going to be putting a category on, not this. But if that's not there, then as a community, we agree that's what we're going to be judging. Okay? We kind of turn a blind eye and go, yes, we accept that it's going to leak. If you remember the third slide, type C, that I showed, where there was a slab, then a big pool of water on top of it, and then another slab. And same with the walls, that's what that is, except they haven't done it here.
Okay, let's jump on to last one. Example number 4. This one, a little bit similar to what we had previously. So we've got a backfilled and drainage system on the outside here. We have a permanent formwork solution core filled with concrete. We do not have any membrane applied to the outside of that. And then we have a cavity on the inside here with presumably a bit of sarking or something like that. This is a drained cavity separating the two. What are your thoughts on this one about how it'll perform, and even some pointers on what you could change to make this a little bit better?
The first thing I would, well, no, they've got to step down. I would say that this is not too dissimilar to the previous design. In the previous design, yes, we had a proper waterproof membrane, but in reality, if we look at the older structures going back 50 or so years or more, they may not have, they more often than not did not actually have a waterproofing membrane on the outer wall. They accepted that it was going to come through. They accepted, they hoped, and often it did work, that it would be collected in this void, and that what we can't see, we don't even think or talk about. And as long as the sarking is working properly, then that wall, which is what you see, you live blissfully unaware, and you go, it's all good. So I would say that that's not too different to the previous one, albeit that the previous one is obviously, because it's got a membrane that goes up, is theoretically more robust.
I might just add one thing to that. I think access, and I think BS 8102 touches on this when it talks about repairability of systems. And I think that's an important note, that really this cavity here, while it does say there's an access vent here that you might be able to stick an inspection camera in or something like that, that's totally different to being able to walk into the plenum and say, hey, I think some moisture's coming in. I'll just go and walk outside and see what it is, and maybe some defect has arisen and you can close that. So while it might not as a fundamental of design be different, that access to do something after the fact, I think it counts for a lot. And
Definitely, yeah. Good point. Absolutely. Absolutely. A lot of the builders nowadays will actually use, for the inner walls, will use like a pre-assembled wall sections that you actually just slip in place. There's a little track which goes down here, and they slip it in place in lieu of basically gain the space. They don't need that access. They just go, well, what we can do is literally just take out three panels. That gives us 6 meters, and we can get a good look, see where this area is that needs more concern, take out that panel and get access to it. So that's something that people are doing nowadays, but that's not necessarily what was happening here. So good point. Thank you, David.
no worries.
Just to add on, would the drain size play a role? Because I'm seeing here it's a roughly like a 50 millimeter drain.
Yeah, so
Opposed to the other one which had a bigger drainage outlet.
yeah, look, that drawing that we saw before where there was a football field in the cavity, hardly ever happens, because space means dollars. If I'd rather have this space I can sell to somebody and get $25,000 per square metre than and just make the maintenance people struggle in a little zone. I mean, we know how it works. So in terms of the ability for that to drain, you need to get buy-in and advice from your geotech engineers. They will tell you what the permeability, the permeance is of the soil, the stratum. You might be building across a dike.
But would it be that the permeability of our primary wall that we need to consider, that we're that wet wall?
Yeah, but you need to go off the concept of, I've done that, so everything's going to be all right.
No.
You've got to say,
We're assuming water's coming in,
yeah.
but how do you assess how much water's coming in to size up the drain accordingly?
Well, let's put it so, I've been in basements where we've had 8,000 litres of water per day. An Olympic-sized pool is 1 million, so it's filling up very, very quickly. it's surprising how much water can come in in a large basement. And so yeah, you need to consider, you need to review geotechnical data, see what they say about the permeance of the area, look at geotechnical faults, because these all play a part in how much water might get in the structure if your barriers don't perform like they seem to perform on paper.
So would you say the drainage should be sized up, assuming there's complete failure of that wall?
Can I answer that one? Because, yeah, I think it... Oh, thank you. That was the last one, by the way. So the way I would look at this is exactly what Sam was saying, but acknowledging that this wall here is going to provide a degree of resistance to the water, right? So if you had 5 litres per minute from a geotechnical perspective, you might say, well, I would expect my wall, and this is very qualitative, right? Like this is where the expertise and judgment comes into a way, because it is hard to quantify, but you might say, well, I've seen a number of these leak before. Here's why they leaked. And if we expected it to go wrong, like it could go wrong, here's the worst case outcome. It's not going to be the full 5 litres a minute that's going to come through. We would expect this much, add some tolerance on top of that, and then do it. But it's a very difficult thing to do. And if I had have had more time, what I would have done with all of these is similar to what we'd done before, right? Put a rating on the outside based on our geotechnical considerations for our exposure to water, and then come through and put some numbers on this and say, okay, we've got a bit of drainage here. That's a degree of protection. We've got a solid structural wall. That's a degree of protection. We've got a gap cavity here, which is actually also drained, albeit a small amount of drainage. That's a degree of protection. And then we've also got a vapor barrier. And you try and give those ratings and then sort of quantify it and make it a more of a quantitative than a qualitative wherever possible. So yeah, and just one more thing, just making sure my team wrote all of that down. We put it in the reports, send it back to our clients tomorrow. Sam Parker Design, full projects done just like that.
David, you also need to mention there's a re-injectable, the hose, there's another,
I did forget to mention that. Yes, that was another mitigation measure which was shown, and there was a re-injectable hose. So if we did find that there was some water coming through, and we could say, okay, let's mitigate that, reduce that down to allow our drainage to perform. Okay, review of a failure. So this is actually a project we've just had come in recently from a client who'd built their home and they're not very happy with the way the basement is performing. And I probably shouldn't be sharing this, but it's worth it for the insight. So this is how it started. The homeowners actually documented this very well, which is really cool, gives me the chance to show it off to you guys. Now, this is the basement, right? So you can see we've got our pile wall here, and then in between, these are the mega flow drains, which we talked about before. So that will allow water which comes down from the top. It stops it from accumulating against the wall. There might be some clay in there or something like that. And it relieves the hydrostatic pressure away from the walls from coming in, right? This is just a top-down view here. You can see that it's a square box, nice and square. This slab down here where it's excavated, it's all one level. There is no pit or anything like that. And we have our mega flows come out and turn out onto the horizontal area there. Shotcrete goes in on top. You can see that the mega flows there, they're extending out from the shotcrete. This is the outcome. And the reason I put this photo in first and foremost is to see that there's a brick wall. So what the build-up is they shotcreted the wall, then they built bricks in front of it. Or they poured the slab, then they built the bricks in front of it. Water coming in, even more water coming in. I don't have great photos of it, this is the best we got. Substantial amount of water coming in. So the question we've got to ask ourselves is what went wrong here? The builder put some mitigation measures in place, right? So let's do a bit of an analysis here. So I sketched this up really quick. The brown is our soil. This section is taken in between the piles, so you can't see the piles here. We've got this red line is our mega flow. This is our shotcrete, which was placed in front of it. Remember, we had the mega flow coming out the bottom here. Slab gets poured on top of it. And then we build our brick veneer on the inside there to finish it all off. So what happens when we have water? This wasn't actually a water table project. You could see it was dry. They didn't have any dewatering in. when it rains, water builds up on the surface, it seeps down through the ground, right? Our drains, megaflow drains, pick it up. They shed water down and they shed it onto the slab. And it goes to about here. And then it just stops. Exactly. We're relying on gravity, but the gravity's not taking it anywhere. There is no pit that you would normally have to pump it out and so on. So what happens? It builds up. It comes up here between the concrete, and then it runs out under our brick wall and into our basement. So pretty simple when you think about it, right? But in this scenario, the builder had built this before and it had worked perfectly. How many of you have had that conversation? I did the exact same thing on the other job. It'll be fine. Totally different situation. There was nowhere for the water to escape to in this particular scenario. And this is what they ended up with. Very unfortunate. Now, this one I've got to, this is the last one I've got, I believe, before I talk about the NCC changes. I have to warn everyone, if it comes across patronizing, this is meant for a lower level audience, which is just entering the industry. So bear with me, don't take it personally. This is a case study on a basement tanking failure. Again, slightly different one. And for this one, I used inspiration from Charlie Munger. He's passed away recently. He's Warren Buffett's lifetime partner, legendary investors. And the reason I bring them up is that I think doing anything correctly is an investment, right? You put in the effort and cost now, and you don't have to pay for it later. And he's got this quote which says, "It's remarkable how much long-term advantage people like us have gotten out of trying to be consistently not stupid instead of trying to be very intelligent." So let's have a look at what that means to us by using this as a case study. So we had a project, very rudimentary design here, but on this project it had a basement, and our blue line here was a continuous barrier. It was a little bit more complex than that, but they had a nice continuous barrier. It was one system. You put it in, you know it's going to connect together and work well, right? So then the site engineers, I don't know who it was, but we'll say site engineers, got together and they started thinking, oh, what about all these other things I've seen before? We can save some cost if we delete that blue line, our waterproofing membrane, from the wall, and instead we'll contractually engage the shoring contractor. Might have been, I think in this case it was a D-wall. We'll put it in their package to make sure that their structure's watertight. And then underneath the slab, we'll get rid of that impervious sheet membrane and we will put in a bentonite sheet membrane because it's more cost effective. Keep in mind what Sam said earlier about bentonite membranes needing to be confined to function. So they all gave themselves a pat on the back and said, yes, let's do this. We've just saved heaps of money and program time and everything like that. And they went ahead and built this. And they've got a reinforced diaphragm wall here. And they've got the bentonite sheet under. And our blue here is a source of hydrostatic pressure. So it's forcing its way up from below. And what happens with our design? Well, okay, so what happened? Well, in this scenario, there was a bit of slab shrinkage for whatever reason. Maybe someone overlooked the size of the pore and how much it would shrink back. But nonetheless, our slab actually shrunk back here. So when it did that, it opened up a gap here, and our bentonite membrane, which was very well confined between these two elements, is now no longer confined. Water, the power of the water, the pressure of the water becomes greater than the swelling properties of the bentonite because it's opened up, and it forces its way up through here. And now we end up with something like I love that music. That's the D wall, a bit rough. Almost all of these are. There's a couple at the end that are from a different project, but yes, all of these are the same project. That's different. That's actually exactly what they did. The problem is that only works when the structure of the slab and the structure of the D-wall are containing the bentonite hard. As soon as they open up, which is what happened, the bentonite isn't contained anymore.
They should have come and grabbed us, the joint.
Oh, yes, and I think they did try to do that. They tried a lot of things. And to build on, Danny, what you were saying, is this the same project? Yes, it is. It was a very big project. And I point this out to say this is the difference between a design failure and a defect most of the time. Defects occur localized due to a workmanship error or a misunderstanding or whatnot. That was a fundamental design failure because they didn't consider an important element of it. And unfortunately, that's the way it ended up. Oh, that's it. Okay. A lot of resin injection is typically the answer. And I have cut it out of this one, but when I presented this, I normally also include a bit of a case study between the difference on what that would have been to do that correctly and what it actually cost. And just to give you a ballpark, millions of dollars worth of resin injection and labor. It's just an ongoing thing. So very difficult. Now, to take this back to what Charlie said, here's some fundamentals on the difference between trying not to be stupid and trying to be intelligent. So someone that's trying not to be stupid, there's nothing that makes us look more stupid than having something fail, right? So what do you do to prevent that? Use tried and tested methods. You understand the level of evidence needed for a design confidence. So not just, oh, that sounds all right. Quantitative evidence and understanding what you should be doing, engaging experts for all those different elements. And this is a very important one, is seeks scrutiny on design to ensure risks are mitigated and intended outcomes are achieved. So I think everyone's been part of a project, a design where everyone's got to put their fingers in the pie and everyone just wants to have a voice, right? And they argue for their point because if their design or their point is the one that gets over the line, it means that they were the smartest in the room, right? Very counterproductive. What you want to be doing is listening to anything that could possibly be wrong with it, taking it on board and making it better. I won't read all these out because I think you've probably read them already. Don't be offended by that one, but I think it's an important lesson, especially for those that are a bit newer to the industry. Okay, to wrap this up, we're going to look at the NCC 2025 changes. And really, the NCC is going to get a lot simpler than it was been, which I think is always a good thing, right? As long as it still achieves the same or better outcomes. So I'm going to start off by reading functional statements, which not everyone really reads, but F1 has been changed, so it's no longer surface water, it's just water, and including any water that may enter the building. So we're wanting to protect it from all kinds of water. And then on the bottom here, we've changed this functional statement. So we've again changed it from surface water to rising damp and groundwater. So it's a little bit more clear. There was a lot of emphasis on surface water before, which was half the reason why below ground didn't get enough attention. The other half of the reason was the exemptions for class 7 and 8 buildings, which Sam covered before. They are also being removed now. So skipping past that, performance requirements. This is really the crux of the NCC. All of the standards and all the deemed to satisfy provisions all just exist as a way to satisfy these performance requirements. And really, there's just been narrowed down to 2 performance requirements. So no longer are we talking about different types of surface water and runoff and this and that. It's been simplified, and I'm not going to read both of these out. I will show them briefly here at the moment, but you can see there's some things have been cut, some things have been added in, but I'm going to skip straight to the point and say this is pretty much how it's going to work. We've got part F1 P1, which is our first performance requirement. That's focused on managing rainwater. And then we've got P2, which is our second performance requirement, and that's largely focused on groundwater. So nice and simple, right? Don't let water above ground into your building in a way that deteriorates the structure, finishes, or impacts amenity. Same thing for below ground. So I think that's awesome. This is actually my last slide, and to look at what our pathways for compliance will be for below ground. We do not currently have a standard. I just sort of made that one up there, but it doesn't exist at the moment. There is no standard. We do talk a lot about BS8 102, and Sam rightly pulled me up before when I sort of said that it's a code of practice, it's not a standard. It is actually a standard in the way that it's written in the document, but it's not a standard in the way that we're used to standards in Australia. To us, a standard is something that shows us how to build and do something very specifically, right? The way that BS8 102 is written, it's still more of a guide and a code of practice, which leads me over to this side here, which is our performance solution. So if we don't have any deemed to satisfy provisions to follow, then everything by default when we have a performance requirement to meet must be met with a performance solution. And this little snippet here is just the guide from the NCC. I know everyone doesn't like performance solutions that much. I think they're awesome, because if you look at all the ways that something could go wrong and all the ways that it performs, and then you put in mitigation measures to stop and deal with all of those, the only possible result you can have if you do that correctly is a good, compliant, performing outcome. So I believe that is my last slide. Any questions, anyone?
Yes.
Yes, go for it.
One question for Sam.
The answer
There
is
you
no.
go.
Okay.
Give me a break.
Now, National Construction the Code 2025 will most likely, require all basements to be waterproof. Now, also we know, the 1st October 2023, NCC 2022 has changed. Now they are requiring, they are basically asking for us to, prevent, the water leaks, the mold mildew, the issues. Now, as we know, insurers, the companies, they are not accepting, mold mildew, water leaks, as well. Okay, so if you are having the basement, it is going to be, NCC non-compliance. If it is water leaking, I'm sure that will basically lead to a lot of litigation. But my question is this: considering all these, the issues, do you think BS 8102 Type 2 and or Type 3 is only solution?
I'm just in the front there.
So there has been some research done on smaller basements where there's airflow that's interconnected from basement to habitable areas higher up. That says that if you had mold that forms at a lower level in a garage, for instance, that it can manifest and spread through to habitable areas of kitchens, lounges, bedrooms, whatever upstairs. So in smaller type structures, I would say the answer to your question is yes. Type 2 and Type 3 would be the only viable option to be able to mitigate or ensure compliance to the mold restrictions you've got. For larger type structures, larger basements, where you've got several recirculation air volumes during the day, I don't see that that's really a major problem. It's rare. I can't think of too many situations where we've had large basements where I've had to deal with legal or complaints that have gone legal about mold forming in those type of structures, but in smaller ones, definitely. That would be my answer to that question.
For everyone's
yes.
understanding, can we call the Type 2 and Type 3 full tanking in a system?
Can we call?
Full tanking system. Full tanking system means, basically you have to, basically protect your slabs and the, the walls, nothing is coming in.
Okay.
That's what the, the 6 councils of Sydney are kind of asking this system.
Yeah. Okay. So that's not actually what a full tanking system means, but I can see why you would say that that's a full tanking system. A full tanking, like a Type C structure, for me is not a full tanking system. Mm-hmm. A Type A barrier or a Type B barrier can be a fully tanked basement system.
That's what I meant with the grade 2 and 3. Obviously,
Yeah.
you have to use Type A.
Yeah. So Type C, whilst it produces the best outcome more often than not, it's not a tanked system. So I hope I've answered that question. I've just got something that I'd like to add to the last slide which David presented. And I might just bring it up just to remind me because I've forgotten what it was now.
Just while you bring up that one, I might just add a little bit onto that. Your question was around local governments requiring tanked outcomes. Does anyone understand, or does anyone want to say what the reasoning behind that is? Why the councils actually ask for tanked basements? You're not allowed to, Sam. Anyone else?
And since some councils are not allowed to, if you're in the water table, there are regulations against pumping the water, so you don't have any other choice.
Because you'd pump it back into the stormwater system, exactly, which is council property. They don't want their stormwater system capacity being taken up by you as an individual lot pumping out water into it, right? So the reason I set the stage on that is that, in my opinion, this might be a hot take, is that even a 1B, which has dampness, that would satisfy the council's objective of not having water pumped out into their stormwater system, right? Because the dampness isn't gonna, you don't need to pump that out.
That's one of the reasons. That's one of the the reasons. But the coming reasons is going to be the small mildew the issues. There are 2 American universities. They made the studies about the transfer of small mildew from basement. The same the dimension. I think it's coming into our legal system fairly well.
I think
We will
that's
see that with the 2025.
Yeah, I think that's definitely a great consideration. Everyone should be more aware of it. I just don't think it's necessarily tied to the tanked basement, the objectives of the local governments
but
at the moment.
The councils are not considering that at the moment because they haven't woke up to that one yet.
Agree?
Yeah.
Yep. Over to
Settled, guys?
Yes.
I was about to jump. Round 2 in another 5 minutes. Okay. No, that's a joke. Great discussion. So I've got a bit of a different take on performance solutions. Even though we don't have a below ground basement, below ground design for waterproofing standard. From my perspective, in my experience in court, the fact that something hasn't got a DTS pathway doesn't mean it needs a performance solution. So that would be my take on it. So let me say this again. The reason you need a performance solution is because you are not following a DTS solution. You haven't chosen to take that path, and so you produce a performance solution which says that my method is going to produce the same level of performance as the cheat sheet, the DTS. In an instance, and there have been several examples, and still is in the code, in the standard, in the BCA, sorry, or the NCC, where there aren't actually standards for certain types of elements of construction, and it doesn't mean that you necessarily need to have a performance solution for it. Definitely, if something went wrong, then they're going to ask for it. It's like the hierarchy of documents from a legal sense is you've got the acts and then the regulations and then the NCC and then the reference standards, primary, and then the reference standards, secondary, and then the non-reference standards, and then the industry norms and good practice. That's the hierarchy. And now I've lost my train of thought. So whilst it's mandatory via DTS to follow a reference standard. So in other words, if you don't build to a reference standard because the reference standard is the DTS, then you could be called up, you could be taken to task for not following the mandatory method of construction, the DTS method. You could be taken to task. If you don't follow a non-reference standard, then that's not a problem until and unless something goes wrong, because what will be put to you is that it went wrong because you didn't follow the standard. It's a play on words, but I'm hoping you're getting the difference. Like, if there's a non-reference standard, I don't need to follow it, but if something went wrong, then they're going to say it went wrong because it didn't follow it. Whereas if there's a reference data and you didn't follow it, then they can take you straight to task and say you should have followed it. There is this thing called consequential loss, which comes into play when you eventually get to court, but that's another level of discussion. So that's just to take that over.
Can I ask you just one more question on that?
Yes.
So when I originally put this slide together, it was more referenced at how we tackle the NCC 2025. And off the back of that, knowing that there's now 2 pretty clear performance requirements, would you expect that the certifiers are going to be saying, show me how you comply with this, prove it to me, and P1, which is above ground, and also P2 below ground, show me how you do that, and what way would they do that? Would it look like this?
Yeah. So there is something which the certifiers, and we've got at least one in the audience, I know. There might be more than one. Stan, looking at you, wherever you are. That certifiers do, not because they have to, but because they're so damn scared of they're so sensitive to things nowadays. So I think that, yes, they will ask you for it. I would argue whether they need to ask you for it, though. But I suspect because of the sensitivities in the industry at the moment, particularly around waterproofing, that they'll say, oh, where is it? Where is your... I mean, I've been asked for performance solutions for roof structures which have been waterproof to 4654.2. Yeah, but Mr. Certifier, read the NCC, you don't need one. No, but I need one because there is just this... It's still a developing concept amongst the industry, I think. Definitely we'll get more clarity once we do have a standard, because then there's no argument. But until then, I think if it gets tested in court, I suspect that it might fall one way or the other, depending on the situation. It won't always fall on the side of you must have a performance solution.
Oh, my turn now.
If this one's for you, David.
No, that's for you, actually. I really enjoyed your slides about the mistakes.
Yes. They were all on your jobs, by the way. Thank you for the photos. Yeah.
Thanks for acknowledging that. The other thing I just wanted to add is that sometimes I see when I go to the sites, and I would like to seek your opinion on that as well, is the location of the CJs, construction joints. Especially with type B, type C, sort of waterproofing, and sometimes with type A as well. So whose responsibility is it to probably specify where the location of the CJs are, the spacing between them, and is it, I can see that a lot of engineers, structural engineers, they don't specify that necessarily. Is it waterproofing consultants, or is it only on the builder? Because as you know, with the fast-paced, just to add that, this fast-paced market that we have these days, people want to go with one pour. I mean, 1,200 square meters. I've seen that in one of the slab on ground to be placed in one go. So, who needs to have some input in that, in your opinion?
Yeah. Do you want to take that, or shall I?
Oh, both of you, please.
Maybe I'll go first, since he was looking at me. There is a strong push now, and has since 2021, that designers must collect themselves and agree a pathway forward where everybody's considerations are put on the table. In other words, integrate the design. This is particularly so with the DBP in New South Wales, Class 2, Class 3, 9C. It's going to be extended beyond that even, and it's now going to go to Victoria, and then it's going to spread even further. So the idea is that the designers should be engaging early on in the piece and saying, these matters are important for me. Okay, but those are important for me. Okay, well, do we need to give a little bit here and take a little bit there to come back to David's concepts of put some numbers to it and go, well, which combination, which permutation gives us the least negative number, right? Or, in Charlie Munger's method, the most positive number, right? If I've sat in a workshop with a very, very, very experienced consultant, and he was putting it on the structure engineer to have this very, very high kicker on the slab. It's great to have a kicker on a slab, by the way. You elevate the joint slightly above, higher up, and so there's less pressure. And the engineer being overpowered by this expert. Oh, okay, I need to do it. I said, no, hold on, wait right there. If you could tell me that increasing the kicker to this point is going to mean that the crack width is going to extend to that much, then the consideration of the waterproofer takes precedence over your consideration, or vice versa, right? You've got to look at what is the risk, what is the likelihood of the risk manifesting, and then what is the outcome, what is the repercussion of that risk, like what David is showing with his AI beautiful slides there. I was saying to some of the gentlemen that were in the ACRA course last week, giving an example, if I was asked to jump over a very wide cavern, very wide gap, very, very wide gap, the likelihood, the chance that I would make it might be low, or the chance that I fall might be high because it's very wide. If in that gap were big cushions, then the impact for me, if I did fail, is not much. So I'm going to react to that risk differently than if that gap was full of needles or sharp objects or flames. I'm then going to need to go, oh no, the likelihood that I'm going to fail is high and the repercussion is really high. So I need some other form of protection. You need to look at that interaction all the time to determine when you've got conflicts of interest as to which one needs to take precedence. It can't always be the architect decides or the structure engineer takes precedence. That does not actually always give you the best outcome.
Yeah, but if you don't specify that it's in the hand of builders, and the builder will do whatever they like to do, especially if they want to do cheaper or they want to do faster, for example.
Yeah, I mean, you saw what David showed, the examples of value engineering. David will tell you better, more articulately than I. Our bugbears are clients will pay us big dollars. Well, David, big dollars. Me, just here, Sam, $20. To give them lots and lots of advice, and we go and we think about it. We contemplate it, we run combinations, permutations, use our experience, all of that stuff, and come back with, this is what you need for your job. They're all good, fantastic, we're signing it off. By the time it gets to construction phase, we don't need that, we don't need that, we don't need that. You don't even know about it, you turn up to, but where's the membrane? Oh, no, we just got a bit of plastic now. That happens, but hopefully with the DBP and other things that are coming in, that are in play now and are gaining more momentum, that is hopefully going to get weeded out a little bit. David, I don't know if you want to...
I just want to add one thing to that. It's definitely collaboration. Everything Sam said was completely accurate, but BS 8102 actually supports this, right? Right at the start of it, it outlines, because this is why I call it more of a code of practice than a standard. It tells you how to go about things and things to consider. It doesn't tell you how to do things. And one of the first things it says is you need to engage relevant parties. So structure, geotech, builder ideally, waterproofing specialist. You had a slide up there before about the waterproofing specialist. That's the first thing it says, and that's not by accident. It's because that coordination is very important. Like the majority of our failures across the industry, don't worry about basements, is just due to lack of coordination between whether it be trades or design and such. And I'll use all the facade guys as an example, because the same thing, we work together on a lot of different projects, and it's that figuring out how to work together and what we like to get that good outcome. It's a negotiation and respecting each other's objectives to achieve that. So yeah. Any other questions, guys? Yes?
What's the expected timeline and process to get an underground structure standard?
That's a good question. So currently the Standards Committee is working, and maybe Sam, you can probably comment a little bit more on this, is focusing on above ground external. There is also scheduled to be a review of the materials standards for internal and external, maybe combining them. And then also on the to-do list is doing a below ground standard. And that's one of the hurdles. We sort of were doing an academic discussion in the AIW technical committee the other day around, well, okay, what would that look like? And we had that same discussion of, you can't just put in BS 8102 and say, yeah, it's our standard. Because everyone's going to open it up and say, well, it doesn't actually tell me how to do anything. It doesn't tell me that in this scenario I should be, doing type A and type B combination measures to get a grade 2 outcome. It doesn't do any of that. So yeah, there's a bit of work to be done and considerations on how to actually do that. Any other questions? That's it. Okay, cool. Well, I think we've had a pretty good run tonight, so I won't do what I normally do and talk about AIW updates and whatnot. We will be having another event, as we do in New South Wales every month. Can't remember what that's going to be next month off the top of my head. That's normally George's spot, but I am sure that it's going to be awesome. So make sure you... Baset's hosting? Excellent. Bayset guys, there he is down the back there. He knows he's got a tall order to fill after some of the events we've had previously, so I'm looking forward to seeing what they come up with. But keep an eye out for us on social media and that sort of thing. You'll see what we've got coming up. And thank you for everyone attending.